Hello everyone. Today we are going to analyze this cantilever beam. In the cantilever beam, any one of the side will be fixed and the other side will be free, and we know that in the fixed support there will be three reactions: vertical reaction, horizontal reaction, then a movement. But in this beam, there is no horizontal load, there is only vertical load. In this case, there will be no horizontal reaction, only there will be vertical reaction and movement. Let us keep the vertical reaction as Ra and the movement as Ma. Let us apply the rule sigma V is equal to 0 and find Ra. Ra is acting upwards so that it will be positive. W is acting downwards so it will be negative. For Ra, we will get W. From the point A, let us take moment about B and find Ma. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. The reaction Ra is acting in the clockwise direction so that it will be positive and the distance is L. Ma will be acting in the anti-clockwise direction so that it will be negative. For Ma, we will get WL. Now I'm going to find the shear force values from the point A and towards the point B. In this case, we have to follow right hand side rule. Upwards will be positive and downwards will be negative. When we find the shear force, we have to only consider the loads and reactions. In the point A, we have a reaction, and in the point B, there is a load. Using them, we have to find the shear force values. When there is a point load or reaction, we have to find the shear force values two times, at just left and at just right. At just left of A, there is nothing. So the shear force at just left of A will be 0. At just right of A, we have the vertical reaction W. It is acting upwards, so it will be positive. At just left of B, only we have Ra. At just right of B, we have Ra and the load W. The load W is acting downwards, so it will be negative. So the shear force at just right of B is 0. Using the values, we can draw the shear force diagram. This is the zero line. On the left of A, the shear force is 0, and on the right side it is W. On the left of B it is W, and on the right of B it is 0. Using these values, we can draw the shear force diagram. Since on the both of the sides we have got the same values, the shear force diagram is in the rectangular shape. Now we are going to find the bending moment values. I'm going to find them from the point A and towards the point B. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. In the point A, we have a moment Ma. If a moment comes, we have to find the bending moment in a point two times, at just left and at just right. At just left of A, there is nothing, so the bending moment will be 0. At just right of A, we have the movement and the vertical reaction. But for the vertical reaction, there is no distance, so we should not consider this. The movement is acting in the anti-clockwise direction, so that it will be negative. Let us find the bending moment at B. Up to the point B, we have Ra and the moment Ma. For this load, there is no distance, so we should not consider this. Ma is acting in the anti-clockwise direction, so that it will be negative. Ra is acting in the clockwise direction, so that it will be positive, and the distance is L. W into L, it will be WL. For the moment at B, we will get 0. We must know that the bending moment at just left of A will be always 0 and the bending moment at the free end B will be always 0. So no need to calculate them and waste the time. Here you can see the bending moment diagram. It is the zero line. We know that the bending moment at the left of A is 0 and on the right of A is minus WL. Since it is negative, we have to make the point below the line, and in the point B, the bending moment is 0. Using these 3 points, we can draw this diagram, and this is a triangle. Using the bending moment diagram, we can find the slope and deflection in the point B. In the point A, there is a fixed support. If there is a fixed support, the slope and deflection will be 0. So only we have to find the slope and deflection in the free end B. We can use the moment area method. The formula to find a slope is area of moment diagram upon EI. We know that it is a triangle. The area formula of a triangle is half into BH. Here the breadth is L and the height is WL. So this is the area. The area divided by EI, we will get the slope in the point B, which is WL square upon 2EI. The formula to find the deflection is area x bar upon EI. X bar is the horizontal distance from the center of gravity to the point B. We know that for this triangle, the center of gravity lies at a distance of 2 upon 3L from the point B. We have to multiply the area with this distance. Then we have to divide this by EI so that we will get a deflection at B, which is WL cube upon 3EI. Alternatively, we can find the slope and deflection at any point of the beam using double integration or Macaulay's method. For that, we have to make a section. I have made a section at a distance of x from the fixed end A. Let us find the moment about this section. Up to this section, we have the reaction W and the moment WL. The moment is acting in the anticlockwise direction, so that it will be negative. The reaction W is acting in the clockwise direction, so that it will be positive, and the distance is x. Then we have to equate the moment to EI d square y upon dx square. Then we have to integrate on both of the sides. These two terms we can integrate using this formula. In this term there is no x, so the integration will be x. When we integrate x, we will get x square upon 2. C1 is the constant. One more time we have to integrate on both of the sides. When we integrate this, we will get y. When we integrate x, we will get x square upon 2. When we integrate x square, it will be x cube upon 3. In this term, there is no x, so we have to multiply with the x. C2 is the new constant. 2 into 3, it will be 6. dy upon dx is the slope. We know that in the fixed support, there will be no slope. In the fixed support, x is 0. In this equation, for x we can apply 0, and for dy upon dx also we can apply 0. In this way, for C1 we will get a 0. Also in the fixed end, the deflection will be 0. Y is the deflection. In this equation, we can apply x is 0 and y is 0. In this way, for C2 we will get a 0. In this equation, for C1 we can apply 0, so that we will get this equation. For these two terms, we can take LCM. We have to multiply this term with 2. We can take EI on the other side. From these two terms, we can take W upon 2 outside. This is the slope equation. We can keep this equation as number 1. Using this equation, we can find the slope at any point of the beam. Now we can take the deflection equation. In this equation, we can apply the values of C1 and C2, which are 0, so that we will get this equation. For these two terms, we can take LCM. We can keep 6 as LCM, So here we have to multiply the numerator and denominator by 3. This is the deflection equation. Using that we can find the deflection at any point of the beam. Let us keep this equation as number 2. Now we are going to find the slope in the point B. At B, x will be L. In this equation, instead of x, we have to apply L. In this way, we will get the slope as minus WL square upon 2EI. Now let us find the deflection in the point B. In this equation, instead of x, we have to apply L. For the deflection, we will get minus WL cube upon 3EI. We have got as negative. That means the deflection is downwards. Also, we can find the deflection and slope in the center. At the center, x will be L upon 2. In the slope and deflection equations, instead of x, we have to apply L upon 2. In this way, we will get the slope and the deflection. This is the elastic curve for the deflection. Here you can see the summary of what we have done. For the deflection at B, we have got this, and for the slope at B, we have got this. Using both of these, we can derive one more expression. Let us assume that the point load is acting inside the beam at a distance of A from the point A. To find the deflection under the point load, in the deflection formula, instead of L, we have to apply A. Similarly, to find the slope, in the slope formula, instead of L, we have to apply A. In the portion CB, there is no load, so the elastic curve will be constant and straight. In this case, the slope will be same from the point C to the point B. We need to find this height. We can use a tan theta formula. Tan theta is equal to the opposite side upon adjacent side. Let us keep the opposite side as y. The adjacent side is L minus A. This angle will be very small. So we can assume that theta is equal to y upon L minus A. But theta c we know. Instead of theta c, we can apply this. We can take L minus A on the other side. It will come in the numerator. This is the deflection at B. This height is equal to this height, which is the deflection at C. And this height we know y. So to find the total height, we have to add this and this. In this way, we will get the deflection at B. From both of these two terms, we can take minus WA square upon EI outside. For these two terms, we can take LCM. Let us keep 6 as LCM. Finally, for the deflection at B, we will get this expression. Now we are going to end this session. Thank you for watching this video.